All right, let's dive right into this explainer and kick off what is essentially a massive detective story. For well over a century, scientists have been obsessed with figuring out exactly what makes up the matter all around us. We've gone from thinking atoms were just these solid, indivisible little spheres to realizing they're actually mostly empty space, just absolutely buzzing with activity. So today, we're going to unpack the architecture of that space. We aren't just looking at what an atom is, we're going to figure out exactly how to track down the most elusive particle in the universe, the electron.
So here's our roadmap for today. We're going to hit 4 main stops. First, subatomic building blocks. Then, measuring atomic size. After that, the quantum number map. And we'll wrap it all up with the rules of electron configuration. Let's get to it.
Starting right off with Section 1, subatomic building blocks, the citizens of our atomic city. Take a look at the hard data here. You've got your protons, neutrons, and electrons, but notice how the electron is just incredibly unique compared to the others? The proton brings a positive charge, the neutron is completely neutral, and the electron carries a negative charge. But look closely at that relative mass column. While the proton and neutron both have a relative mass of roughly 1, the electron is just a tiny fraction. It's literally 1,836 times lighter than a proton. I mean, that is almost zero mass. It's essentially this nearly weightless little speck of pure electric charge just zipping around a really dense, heavy center. Now, what's really wild is actually seeing that data in action. Watch how that incredibly light electron is deflected so wildly by the electric field compared to the heavy proton, while the neutral neutron just sails right on through. Because the electron is negatively charged, it arcs super sharply upward toward the positive pole. The proton, being positive, curves down toward the negative pole. But notice how its curve is way shallower? That's because, remember, it's 1,836 times heavier. It has way more inertia, so it's a lot harder to pull off course. And the neutron? Completely unaffected by electric fields. It just cruises in a straight line. This fundamental difference in mass and charge pretty much dictates everything about how atoms interact. Moving right along to Section 2, measuring atomic size, or what we can think of as the borders of the city. This is where we see a really fascinating tug of war. The size of an atom isn't some fixed, hard boundary. It's basically determined by the average distance from the nucleus to the outermost electron cloud. When an atom loses an electron to become a positively charged cation, it visibly shrinks. And why is that? Well, you've got the exact same number of positive protons pulling on fewer negative electrons. The effective nuclear charge overpowering the electrons increases, which pulls that remaining cloud way tighter. On the flip side, when an atom gains electrons to become an anion, it bloats out. Those extra electrons increase the repulsion in the outer shell, pushing everything further apart, even though the pulling power of the nucleus hasn't changed at all. And this graphic perfectly illustrates those periodic trends. You can visually see how the atomic radius shrinks as you move left to right due to that nuclear charge, but then it expands as you go down a group because you're adding whole new shells. Think about it. If you look at the rows moving left to right, you're adding protons and electrons to the same general shell. More protons mean a stronger magnet in the center, pulling that shell inward, which shrinks the atom. But when you move top to bottom, you are adding entirely new layers, new shells, which physically shield those outer electrons from the nucleus's pull, making the atoms universally larger. So this brings us to a huge turning point. Because as spectral analysis got better and better, it became super clear that Bohr's simple rings just weren't enough to actually locate our elusive electrons. The old model pictured electrons orbiting the nucleus exactly like planets around the sun. But as scientists developed high-resolution spectrophotometers, they noticed the light emitted by atoms was splitting into these fine, incredibly complex lines, especially under magnetic fields, which is known as the Stark and Zeeman effects. A simple circular orbit just couldn't explain that kind of complexity. The electrons weren't on neat little train tracks. They were existing in these complex three-dimensional clouds. Which leads us perfectly into Section 3, the quantum number map, basically our cosmic address system. Think of these 4 quantum numbers as the ultimate cosmic address system. It's like giving you the zip code, the street, the specific house, and finally, the exact room number of any electron. No matter how massive the electronic cloud gets, these 4 numerals are all you need to specify an exact location. The principal number n is your main shell that dictates the overall size and energy. The azimuthal number L dictates the shape of the subshell. The magnetic number m tells us how that shape is oriented in 3D space. And finally, the spin number s identifies the specific electron living in that space. So let's zoom in on the azimuthal number for a second. This is absolutely crucial because it tells us the actual shape of the space where you are most likely to find the electron, whether that's an s, p, d, or f orbital. Instead of a flat circle, an s orbital is perfectly spherical. A p orbital looks more like a dumbbell stretching out along an axis. And the d and f orbitals, they get even more wild and complex, looking almost like multi-lobed balloons. This quantum number, which ranges from 0 to n-1, proves that our atomic city has some very distinct architectural styles, depending on exactly which neighborhood or shell you happen to be in. Now let's look at the final piece of the address, the spin quantum number. This answers a really big question. How can two electrons share the exact same room without canceling each other out? Well, they do it by simply spinning in opposite directions. Back in 1925, scientists proved that electrons actually spin on their own axis, and that creates a tiny magnetic field. Because electrons are negatively charged, putting two of them in the same orbital should mean they repel each other violently. But if one spins clockwise, giving it a positive 1/2 value, and the other spins counterclockwise with a negative 1/2 value, their magnetic fields perfectly cancel each other out. It's a really elegant solution that allows exactly two electrons to peacefully coexist in a single orbital space. Okay, bringing it all together in Section 4, Rules of Electron Configuration, or how we actually fill up these atomic houses. The Aufbau principle is basically our ultimate roster guide. It ensures that electrons always fill the lowest energy houses first before they start moving into the higher energy real estate. Nature is fundamentally lazy, right? It always prefers the lowest possible energy state for maximum stability. So electrons will completely pack out that small spherical 1s shell closest to the nucleus first, then they move to the 2s, then the 2p, and so on. Interestingly, though, because of how these energy levels overlap, they'll actually fill the simple spherical 4s shell before they go back to fill the complex lobed 3d shell. It's a really strict mathematical hierarchy, and it governs every single element in existence. Now, if you're wondering how we know all this configuration math is actually real, well, we can prove it by looking at emission spectra. These are the unique flashes of light released when electrons jump between these very specific energy levels. When you pump an atom full of heat or electricity, its electrons absorb that energy and jump up to higher, empty shells. But they can't just stay there. When they fall back down to their proper address, they release that exact packet of energy as a photon of light. And because the distance between the shells is mathematically exact, the color of the light is exact too. Hydrogen creates its own distinct spectral lines, while sodium emits a very characteristic bright yellow line. This isn't just a theory on a chalkboard, it is observable reality. So I'm going to leave you with this one final thought to ponder. How does mapping this incredibly tiny, completely invisible atomic world give us the exact tool we need to analyze the composition of distant stars across the cosmos? Because by understanding this cosmic address system, by knowing exactly how electrons configure themselves and the specific colors of light they emit when they move, we can look through a telescope at a galaxy millions of light years away, analyze the light spectrum it emits, and know with absolute certainty whether it contains hydrogen, helium, or iron. The smallest map we possess is literally the key to decoding the largest mysteries of the universe. Thanks for hanging out with me for this explainer, and keep exploring.